Section 8.3 Part B, when sigma is unknown, the t-distributions. The t-distribution, also known as student's t-distribution, is a probability distribution that is used to estimate the population parameter when the sample size is small and or when the population variance is unknown. So why use the t-distribution? According to the central limit theorem, the sampling distribution of a statistic, like the sample mean, will follow a normal distribution as long as the sample size is sufficiently large. Therefore, we know the standard deviation of the population. We can compute a z-score and use the normal distribution to evaluate probability with the sample mean. But sample sizes are sometimes small, and often we do not know the standard deviation of the population. With either of these problems occur, statisticians rely on the distribution of a t-statistic, also known as the t-score, whose values are given by the formula of t is equal to x bar minus the mu all over the standard deviation of the sample divided by the square root of n, where x bar is the sample mean, mu is the population mean, s sub x is the standard deviation of the sample, and n is the sample size. The distribution of t-statistic is called the t-distribution or the student t-distribution. The t-distribution allows us to conduct statistical analysis on certain data sets that are not appropriate for analysis using the normal distribution. So when you go to use your t-statistic, you have to know your degrees of freedom. The statistic t has the same interpretation as any other standardized statistic. It says how far x bar is from the mean mu at the standard deviation units. There is a different t-distribution for each sample size. So we specify a particular t-distribution by giving its degrees of freedom. When we perform inference about a population mean mu using a t-distribution, the appropriate degrees of freedom are found by subtracting 1 from the sample size. So your degrees of freedom is always n minus 1. We write the t-distribution with n minus 1 degrees of freedom as t sub n minus 1 for short. The t-distribution can be used with any statistic that is approximately normal. The sample distribution of the statistic should be bell-shaped if any of the following conditions apply. So the population distribution is normal. The population distribution is symmetric, unimodal, without outliers, and the sample size is at least 30. The population distribution is moderately skewed, unimodal, with outliers, and the sample size is at least 40, or the sample size is greater than 40 without any outliers. The t-distribution should not be used with small samples from populations that are not approximately normal. So you can either do, if it's approximately normal, you can do whatever sample size you want. If the population is not normal, then you cannot have a small sample. The more normal it is, the smaller the sample size can be. If it's not normal at all, or it has outlier, or if it's not normal, then it has to have a sample size of greater than 40. If it's moderately skewed, then you need to have at least 40. But if it's symmetric, unimodal, then you can just have at least 30 instead. So if you draw a simple random sample of size n from a large population that has a normal distribution with a mean of mu and a standard deviation of sigma, the statistic t is equal to your sample mean minus the mean of your population over the standard deviation of your sample divided by the square root of your sample size. And your degrees of freedom is n minus 1. This statistic will have approximately a t sub n minus 1 distribution as long as the sampling distribution of x bar is close to normal. So in this picture, we're going to have different degrees of freedom. So your standard normal curve is the one that's in the purple. If you have the red one, that's if we have degrees of freedom of 2, which means our sample size is only 3. And then the other line is if we have degrees of freedom of 9, which means your sample size is 10. As you can see, as the sample size gets larger, it becomes more and more normal. So the figure above compares the density curve of the standard normal curve to a distribution for degrees of freedom of 2 and 9. That previous figure illustrates the facts about the t-distribution. The density curve of t distributions are similar to the shape of that standard normal curve. They are symmetric about 0, single-peaked, and bell-shaped. The spread of the t-distribution is a bit greater than the standard normal distribution. The t-distribution in the previous figure have more probability in the tails and less in the center than the normal standard curve. This is true because substituting the estimate for the sample standard deviation for the fixed parameter of the standard deviation for the population introduces more variation in that statistic. And as the degrees of freedom increases, that t-density curve approaches the standard normal curve even more closely. So the larger the sample size, the more normal it's going to be. This happens because the sample standard deviation in place of the standard deviation for the population causes a little extra variation when the sample is large. The table B in your packet of information gives critical values T star for the t-distribution. Each row in the table contains critical values for the t-distributions whose degrees of freedom appear at the left side of the row. For convenience, several of the more common confidence levels in percents are given at the bottom of the table. By looking down any column, you can check that the t critical value approaches the normal critical value z star as the degrees of freedom increase. So when you're using table B, suppose that you want to construct a 95% confidence interval for the mean mu of a normal population based on a simple random sample of size 12. What critical value t star should you use? So if our n value is 12, remember your degrees of freedom is 12 minus 1. So if you look at the table or table B, you would go to your degrees of freedom of 11 and you would find your 95% confidence interval at the bottom. Where those two meet will tell you your t star value or your critical value for the t distribution, which in this case would be 2.201. The desired critical value, again, your t star would be 2.201 if your degrees of freedom is 11 and your confidence level is 95%. In that previous example, notice that the corresponding standard normal critical value for the 95% confidence interval, not 96, is z star is 1.96. We have to go out further than 1.96 standard deviations to capture the central 95% for the t distribution with the degrees of freedom of 11. So your calculator can do this for you as well. If you press second and then the vars button, which gives you distribution, and choose option 4, which is the inverse t, you can enter the area as a decimal and the degrees of freedom, and then select paste and hit enter, and it will do the calculation for you. But using table B to find the critical value that you would use for the confidence interval for a population mean mu in each of the following situations. So a 98% confidence interval based on a sample size of 22 observations. Again, on your table, because our n value is 22, you would have to look up a degrees of freedom of 21, because our degrees of freedom is n minus 1, which is 22 minus 1, or 21. Now, if your degrees of freedom is not on your table, you would have to look at the next smallest number. So if you do not have a 21 on your table, you would have to look at degrees of freedom of 20. You can't go larger than what's on there. You can only go smaller. But if you look up a 98% confidence level with a degrees of freedom of 21, you should get a t-star value of 2.518. This time we want a 90% confidence interval with a sample size of 10. Again, our degrees of freedom will be 10 minus 1, which will give us 9. So we'll look up a degrees of freedom of 9 with a 90% confidence interval on table B, and you should find your t-star value as 1.833. If we have a 95% confidence interval for our sample size of 7, Your degrees of freedom in this case will be 7 minus 1, which is 6. Our confidence level is 95%, which should give you a t-star value of 2.447.